Hi, we are discussing the concept of linear regression, and this is the second part of the lecture. If you are new to this topic, I strongly suggest you first go through the first part, and the link is available in the description box. So we are actually using a straight line to form our linear regression model. Through an example that our model needs to learn the relationship between a person's height and weight. It turned out to be that, as we know that there is a linear relationship between height and weight, the linear line was able to capture that given these two blue data points. Whereas the KNN model was not able to catch this relationship. So the summary is a straight line has two parameters, beta 0, which is the intercept, and beta 1, which is the slope of the line. Okay. So when we'll be talking about what are the model parameters of a linear line, we are talking about beta 0 and beta 1. Sometimes we may describe through theta, but you need to remember these two parameters. Okay. So now we will move from this linear line to linear regression. We'll use the same two data points. We draw a linear line, but the problem becomes when we have more than two data points. For example, here we have 4. And it is very unlikely that all these 4 points will sit on the same line, right? And whatever way we may try, we can draw an infinite number of lines, but no line will go through all those 4 points. For example, this one, this one, this one. So we need to learn something that will best capture the relationship given these 4 data points. So that's the general idea of linear regression. For example, here we have a model that we represent as black theta. And then we have an orange model. It has its own intercept and slope. We need to quantify that which model is actually better. So that's the first thing that we need to learn. One idea might be that, okay, this black line is not going through any of those 4 points. However, the orange one went through 2 points. So I choose the orange one. Okay. So that's a good strategy, but we need something that is quantifiable. So that's the first thing that we need to make sure. Okay. One thing that we can do is the absolute error made by each of our models. Okay, in this case, we are evaluating the first model, and it turned out to be that for the first point, the model is making E1 error. Okay, but if we ask to level this data point by this model, then it will at best can say that it is here. Okay, so this is the error. Okay, for the second point, you have error 2, third point, error 3, fourth point, error 4. Okay, now we sum them over. So this will be total error of this model. We do the same for the orange model, and it turned out to be that for the first point, the model has 0 error, second one E2, third one 0, fourth one E4. Okay, and this will be the total error of the orange model. So which one is better or favorable? Because this orange model has less error than the black model, so our preference would be the orange model. Now we have to generalize this for any number of points and any number of models. To do that, first we need to learn some definitions. Okay, so for example, the model theta, beta 0 and beta 1, when we will be referring to this, we are talking about a line or a linear regression model. Okay. And then prediction function, where does the model predicts for a new data point, and your parameters. Okay. Then the fitting error, in this case the absolute error, so where the model predicted and where was the original data point, their alone distance. And then we will need to define a function, what we call optimization function, loss function, or error function. Okay. And how do you define that? We are saying that the error of a model with parameter theta equal to 1/2, then you sum over all your data points. So here this is an absolute error, but here we are using a quadratic error. Okay. N is number of training data points. So in this case we have 4. Okay. From 1 to 4, what is the deviation of my model's performance squared, and then I sum them and then take the half. Okay. Why we took the half, I will explain in a while. Okay. So this is what we are calling the error function, and this is our optimization or objective function. And how do I read it? So my target is the theta that minimizes this function. So that's the general idea. We can solve this equation or solve this optimization function by using some linear algebra techniques. For example, ordinary least squares, where you just need to do some matrix operations, but that's not the scope here today. We will need to learn some general technique that is applicable to many other machine learning tasks. So let's summarize. So we want to actually generalize this setup because we want to learn our solution for any number of points. To do that, we will need to learn some definitions. So this is our model, and then this is our prediction function, y hat equal to beta 0 plus beta 1 x, and then we define some error functions. This absolute error function, and this is our objective function. Here we want the theta that minimizes this error function. Okay, and in this case this is a quadratic error function. Before I go to the algorithm, we need to estimate the derivative for each of those parameters. So this is our error function, and then we plugged in the prediction function here. So this is the prediction function, this is our label, and then if we take the derivative with respect to beta 0, so if I do the derivative of my error function with respect to beta 0, then what will happen? 2, if you take the 2, then 2 and this 2 will cancel, and this will be the derivative. Okay, and that's why we took half. Okay, you can do the derivative by yourself and check with these values. Okay, if you do the same with beta 1, then the value will be the same, but you have to do the multiplication with x1. Okay, because here we have xi multiplied with beta 1. Okay, but you can check with the math. Okay, if you are unsure, please let me know. Okay, we call this as partial derivative because if you recall, y equal to x square, if you do the derivative, then it is 2x. We are already aware of that. Here our function is actually a multivariate function, beta 0 and beta 1, right? So literally, if we do actual derivative or full derivative, we have to do in regards to both at the same time. But here we are not doing that. We are doing partial derivatives. That means we are estimating the derivative per axis. So again, this is the error function. You can check with the derivative and let me know if you have any questions. Okay, or if you are unsure about anything, let me know. In the next part, we will be discussing the gradient descent algorithm, but you will require to understand what is objective function or error function and how to estimate the derivatives.